For the limit as x approaches negative infinity of x times the natural log of 1 minus 1 over x, when we perform our check, what we get is a form that looks like negative infinity times 0. Remember, plugging negative infinity into x in a denominator is going to make that term equal to 0, and the natural log of 1 is 0. So we have a different type of indeterminate form in this case. And when we encounter an indeterminate form that's a product of 0 and infinity, then, or negative infinity, then we will work to express the product as a quotient. And so we're going to write down the limit as x approaches negative infinity of the natural log of 1 minus 1 over x divided by 1 over x. See, what we've done is we've turned this factor of x into a denominator of 1 over x. And you can verify that multiplying by the reciprocal of 1 over x will yield a factor of x. At this point, I'd like you to pause the video, apply L'Hopital's rule, and see what you come up with. Well, the derivative of the natural log is 1 over the argument times the derivative of the inside function, which in this case is going to be positive 1 over x squared. Thought it was going to be negative because 1 over x has a derivative that's negative, but it's preceded by a minus, and so that's a plus. In the denominator, we've got 1 over x, which differentiates to negative 1 over x squared. The 1 over x squared in the numerator and the 1 over x squared in the denominator divide out, leaving us with a negative factor. And we have simply the limit as x approaches negative infinity of 1 over 1 minus 1 over x. That's going to be a 0 for the 1 over x in the denominator. We have 1 over 1 with a minus sign in front, and so our answer is negative 1. Now, you just saw an example of me catching a mistake in real time. I thought I was right, and it turns out I was wrong. The way I knew, folks, is because I went over it again. And looking again at that negative 1 over x squared, I saw I need to change that sign here. I only go through that to say, look, this is something you can also do when you're taking an exam. You don't need to verbalize it, and in fact, if you're in a classroom, of course you don't verbalize it, but what you do is you look back over all the steps you've written and see if you can catch any of the careless errors. See if you can catch them, I don't have to. Next, we have here the limit as x approaches 1 from the positive side of the natural log of the quantity of x to the 7th minus 1 minus the natural log of the quantity of x to the 5th minus 1. Performing our check, putting 1 in place of x, we're going to end up with negative infinity minus negative infinity, or negative infinity plus infinity. This is an indeterminate form. One way to look at it is, if I have infinity minus infinity, I don't know which infinity is bigger, and so I don't know which one will win. I had said in a previous video that oftentimes when we see infinity minus infinity, we're going to get common denominators. That is not the case here. The case here is that we have natural logs, and we have a difference of logs. And so by applying properties of logs, we can say this is the limit as x approaches 1 from the positive side of the natural log. Well, I wrote that little. One big natural log of x to the 7th minus 1 divided by x to the 5th minus 1. This may look like a good candidate for L'Hopital's rule because I have x to the 7th minus 1 over x to the 5th minus 1. However, the limit is applying to a single function, which is a natural log. So I cannot actually apply L'Hopital's rule to this expression here. So what we're going to do is we're going to invent an L equals. So we're just going to set this limit equal to some number L. Let me move that over so I have a little bit of room there. And once I have that L is equal to a natural log, we can actually exponentiate both sides. So at this point, I'm going to make both sides the exponent on the base e. Now, a limit essentially passes through a continuous function, and an exponential function is continuous. On the left-hand side, we have e to the L, which we'll deal with later. On the right-hand side, I can write the limit as x approaches 1 from the positive side of e to the natural log, those cancel. So the limit is now being applied to x to the 7th minus 1 over x to the 5th minus 1. So what we've done is we've used a cancellation property between exponentials and logarithmic functions to simplify the expression on the right-hand side. The reason for the L on the left-hand side, at this point I'll say it's a reminder at the end of the problem that we're going to have e to the L, and so it's a reminder to solve for L, not to leave it as e to the L. Well, e to the L in this case, applying L'Hopital's rule, will be the limit as x approaches 1 from the positive side of 7x to the 6th divided by 5x to the 4th. Directly substituting 1 in place of x is going to give me that e to the L is equal to 7 over 5. Now, dealing with the fact that we have e to the L on the left-hand side, if we apply the natural log to both sides, we end up with L is equal to the natural log of 7/5. That's our answer. So in this case, infinity minus infinity turns out to be the natural log of 7/5. Who would have guessed?